We now take a look at a second way that the area problem can be generalized, right? And in fact, this particular problem, it kind of flips, literally, it flips the area problem on its head and then gives it a twist, right? So a flip and a twist. Sounds exciting. Well, let's see what it's all about. Now, so far, when we've talked about the area, it's always been about functions of the form y equals f of x. But why does y have to be the dependent variable? Why can't we switch the roles of x and y? And let's see what that would look like. In fact, what I'll do, let me just start with a sketch. So instead of saying that the y value depends on the x value, what if we flip it around? Like literally keep the axes the same, but now say that the x value depends on the y. So it's almost like now our domain is on the vertical axis and the range is on the horizontal axis. So those types of equations look like this. I mean, it's a simple change to something like this, right? X equals g of y. So what would happen is I would pick my y first, figure out the corresponding x, plot the point, and repeat that for several y's that are in the domain of this function, and then I would have a curve, presumably, that looks like this. And then our limits now would be on the y-axis. So my limits would be, let's say, from C to D. I don't want to use A and B in that regard. We typically use A and B as the interval for x. I'm going to use different letters, a different pair of letters to reflect the interval on the y-axis. And then, so the idea that the area, this region, right, if we think of now, what is the area between the curve and the y-axis, so this, right, so all we would do is, if in fact, let me write it in blue to say the blue area is given by this definite integral from C to D, and what would I integrate? I would integrate g of y with respect to y, right? Now, I'm not going to go back to the formality of all the Riemann sums, but essentially our rectangles would now be horizontal as opposed to being vertical, right? So that's an easy flip, right? That's an easy flip. It's like everything just switches. What was in terms of x is now in terms of y, right? But then let's take what we did previously and say, well, what if we have not one of these functions, but what if we have two? So let me now describe to you our second take on this area problem. So suppose W and V are continuous functions of y, right? So are continuous functions of y on the interval c less than or equal to y less than or equal to d, right? Such that, and I'll write down a very similar inequality as we did in the case of when our area was with respect to x. So such that, let's say that w of y is greater than or equal to v of y for all y's in this interval. So for y in that interval, right? Well, graphically, what does that mean? Since we're now talking about the x value being the dependent variable, so if I were to graph these two, if this function is greater than or equal to this function, so if w of y is greater than or equal to v of y, then if I plot both of them, I would expect the x values on this graph for w to be greater than or equal to the x values on the graph of this function. Now, as far as having a bigger x value, that shows up by something that's further to the right. On my x-axis, the bigger the x, the further to the right you are, right? So now we could say, so let's kind of describe that before we draw the graph here. So this means, right, the graph of x equals w of y is to the right of the graph of x equals v of y. It's to the right of the graph of x equals v of y. And at most, they can touch. So moreover, the graphs may touch, right, but not cross. Again, because of the inequality, right? So that at most they might be equal. Otherwise, this graph is going to be further to the right, right? So the graphs may touch, but never cross. All right. So now let's put this all together and see what we have, right? So let's draw. There's our y. There's our x. So now again we're saying that here's our domain. It's on the y-axis. Let's say from C to D. And here is the graph of x equals w of y. And now I'm going to draw the graph of x equals v of y. But again, just to emphasize this latter point that the graphs may touch but never cross, one possibility, now I'm not going to sketch all, is something like this, right? Something like that. And again, this one is x equals v of y. And our goal is to now find the area between these two. Right? So to find that blue area, right? Well, the principle behind it, there's a formula for this. The principle behind it is identical to what we did for a region between two graphs that were in terms of x, right? So what we would do, take this big area, or I should say the area from the curve on the right down to the y-axis. So take all of this, right? And we know how to find it. This is what we stated earlier. So that area in red, let me write the definite integral in red so you'll make that association. So C to D, if I integrate the w function, right, I will get that area that I have shaded in red. But because I want just the blue, I would then have to take away the green. So I would have to take away the area that's to the left of the V curve, right? So I'd have to do minus this integral, the integral from C to D of V of y dy, right? Same approach, take the area of the big region, and that big region would now extend out to the function that's further to the right, and subtract the area that's between the function on the left and the y-axis, and I will be left with what's in between the two, right? And this is how we normally write it. So let me say, therefore, this area now in blue is the integral from C to D of w of y minus v of y dy, right? So the form of the definite integral is very similar. What's different is the fact that now we're integrating with respect to y. So the region now goes across to the y-axis, right? And often, now based on the positioning, I often refer to w as the function on the right. So the right function, because it's further to the right, it has the larger set of x values. So I usually call this the function on the right. And then this function over here, the smaller of the two, obviously is the function on the left, right? So this one kind of forms the left boundary, this one forms the right boundary, and for the area between them, this definite integral solves the problem, right? So basically, I mean, the main shift is really is in our perspective and our mindset, because as far as the process, it's still a definite integral. We're still taking the difference of two functions. We still have a pair of limits. It's just that now all of this is in terms of y, not x. All right, so let's see if we could take an example of this and see what we can make of it, right? So let's say, so here's our example. And so I'll write it out. Find the area of the region enclosed. Sometimes you see it worded like this. Instead of bounded, it might say enclosed by. And now here are the equations. X equals y squared and y equals x minus 2, right? Now, when you look at this, the way this question is written, it's almost like it's forcing you to make a choice. Do you think of this as a function, or a function in terms of x, right? Or a function in terms of y? So it's like one is in the form x equals, and the other one is in the form y equals. But that's just algebra. We can rewrite these however we want, right? In fact, I think what we should do, let's sketch this region, right? Let's sketch this region and then figure out if we could express it in terms of y, to like express everything in terms of y and find the limits on the y-axis, right? Now, usually for sketching, because most of the graphs that you've sketched are in the form y equals f of x. And if that's easier for you, then you can write this in that form, right? And use those forms of the equation to generate the sketch. And then based on the sketch, we can see, okay, is it easier to integrate with respect to x, or is it easier to integrate with respect to y, right? So so this one is already in the form. I mean, this is, we know that this is a linear function with slope 1 and y-intercept -2. This one, it looks like a parabola, but it's flipped, right? This one is x in terms of y. Now, it's not hard to see that if I sketch this graph, right, because x is equal to y squared, no matter what no matter what y is, x is always going to be positive. So we would expect the graph of this function to be in the first and fourth quadrants, because that's where x is positive. So this is a parabola, but instead of the parabola opening up, it's going to open to the right, right? Because that's where our x values are all positive. So it's going to have the shape of a parabola that looks like this, right? And it's x equals y squared, right? And we don't need it in this particular problem, but if there were constants added here, you would have the same kind of shifting. You could shift this parabola that's oriented or opened to the right. You can shift it further to the right. You can shift it up, down. You can shift it to the left. And it all depends on where you put the constants, right? But that's not something that we need, because we want the basic parabola. Now let's sketch the line. So we know that this line has slope 1, y-intercept. So let's say that's -2, and it has an x-intercept of 2 as well, because when x is equal to 2, y is equal to 0. So it's something there. And actually, let me put this further down, put that there, connect them, right? So that's the line y equals x minus 2. And we can now see the region that is enclosed by these two, right? So, and in fact, what I'm going to do when I shade this, I'm actually going to shade it horizontally. I'm going to shade it with horizontal stripes, and it starts from the smaller y's. Again, we know that this one is to the left, so it's the x values on this curve are less than or equal to the x values on the line. Right? So as far as right and left, the line is the rightmost function, right? And then the parabola is the leftmost function. You can even put that in parentheses, just so when we set up our definite integral, we have it in the right form. So this is the function on the right, and this is the function on the left. All right. So it seems like all that's left to be determined before we can set up our definite integral are the limits. And again, I am going to be looking for limits on the y-axis because I want to find my c and d, right? So in order to do that, now, so basically what I've been doing, I think I've like even subconsciously made the decision that I am going to do my integration with respect to y. That means I have to switch this equation into the form x equals a function of y. So from this, I need to solve for x. Now that's pretty easy. Add 2 to both sides, and here will be the equivalent form, but now writing x as a function of y. So it looks like that. So basically, we can start setting it up. We can start setting it up. It's going to be a definite integral, and I have to figure out the limits, but at least I know what the integrand is going to be. It's going to be the function on the right, which is the y plus 2, minus the function on the left, which is y squared. And we're going to integrate with respect to y, but now I have to figure out the y limits. To figure out the y limits, I have to figure out where these curves, or where the curve intersects the line. So what I'm going to do is set y plus 2 equal to y squared and solve that equation for y. So let's do the algebra on this side. Right? So we're going to find the points of intersection. I mean, we can see that they intersect, right? It's just a matter, we need the specific numbers, right? We need those specific y values. So points of intersection, so set the y plus 2 equals y squared. And what I'm going to do is turn this into a standard quadratic equation by moving all the terms to one side. I prefer having a leading coefficient that's positive, so I'm going to move the y over to the right and the 2 over to the right, so the equation becomes this: y squared minus y minus 2 is equal to 0. And what's really nice is this one factors. This factors as y minus 2 and then y plus 1, right? So we can get our points of intersection right away. So the 2 points of intersection, either y is equal to 2 or y is equal to negative 1. So the smaller of the y value clearly is down here, right? Clearly this is where the negative 1 would be, and then the 2 would be my upper limit. So now I have all the ingredients that I can use this alternative approach, right, to find this area, but integrating with respect to y as opposed to all the previous integrals that we've done, which were with respect to x. So put the negative 1 as my lower limit, the 2 as my upper limit, and then we integrate, right? So now I don't technically need the parentheses there. I just did that for emphasis, right? So you could certainly write it like that. Also, if you know, are kind of a stickler for having your quadratic written in decreasing powers of x, then you can certainly put the negative y squared first, and then y, and then the plus 2, right? So you could certainly do that and integrate it. But whichever form, these are all equivalent. And now, so let's do the actual antiderivative. So that is negative 1/3 y cubed plus 1/2 y squared plus 2y. And now, using my FTC, we have our limits to plug in, and then we're going to take a difference. All right, let's see what we have. So at the upper limit of 2, so 2 cubed is 8, and 8 times negative 1/3 is negative 8/3. And then y squared is 2. So 2 squared is 4 plus a half. I'm sorry, not plus a half, times a half. That's 2. And then 2 times 2, that's 4. So that's what we get at the upper limit. And then minus, let's see what we get at the lower limit. When we cube negative 1, we get negative 1. Negative 1 times negative 1/3 is a positive 1/3. Negative 1 squared is a positive 1 times 1/2 is positive 1/2. And then we have 2 times negative 1, so that's minus 2, right? And then let's see. So it looks like we're probably going to need a least common denominator of 6. So let's do that. So we will have negative 16 over 6 plus 12 over 6 plus 24 over 6 minus 2/6. I'm also going to distribute the negative sign. And then minus 3/6 minus 12/6. Plus, actually, right? Distributing that negative sign. So denominator of 6, let's do some addition. So negative 16 plus 12, that's 4. Plus 24, that's 28. Minus 2 is 26. Minus 3, that's 23. Plus 12, that's 35. So 35 over 6. Let's see. Did I do that correctly? Actually, nope. I made an arithmetic error. This is actually, let me fix this. This is actually 27 over 6. Yep. So 27 over 6, and then that reduces to 9/2. And again, if you wanted to put units squared for area, you're more than welcome to do so, right? So that's what it looks like. Very, very similar in terms of, you know, the algebra that we might have to do as far as finding points of intersection. The antiderivative rules are exactly the same. Again, as I said earlier, it's just a matter of changing our perspective and getting used to the idea that now you can have your x value be a function of y, right? See you later.